Hi everyone, this is my first English video, and just so you know, I used AI to generate the voice. This episode will discuss position tolerance for threaded holes, and the selection of appropriate GD&T and modifier symbols. Alright, let's talk about Mr. Jakob Hartung's LinkedIn question about spotting 0 at MMC on a threaded hole. I've checked out Jakob's example drawing and made some revisions. There's a bunch to talk about, and I can break it down into 4 or 5 episodes focusing on GD&T. Today, in this episode, I want to talk about how to control the position of threaded holes. So from the drawing, it looks like we're probably dealing with a bolt that goes through that hole on the left. Basically, the hex socket head cap screw is that part. In this design, the fasteners will act like an interference fitted into the threaded holes to ensure a secure fit. Moreover, suitable clearances must be preserved between the fastener shaft and head and the corresponding through holes. Consider the dimensional relationship between a socket screw and a threaded hole. As the picture shows a socket screw going into a threaded hole, we will see the major diameter of the hole is bigger than the minor diameter of the screw. So we can clearly see that those diameters aren't actually the points of contact we're looking at here. Just so you see, the threaded hole's minor diameter and the screw's major diameter are not actually where they touch. What part actually connects the socket screw to the threaded hole? Basically, when you screw a socket screw into a hole, the screw's spiral teeth connect directly with the hole's spiral groove. The helical surfaces are represented by their pitch diameter, an imaginary cylinder. This serves as the default control element when applying GD&T position tolerance to the threaded holes. The assembly scheme showed the screw with a nominal diameter of 12 millimeters. The clearance hole diameter measures 13 millimeters, so the socket screw has a maximum positional deviation of 0.5 millimeters. Alright, we've got a 1 millimeter cylindrical tolerance zone for the GD&T position. Simple as that. Just ignore the datum reference for now. We'll get to that later. Let's break down this GD&T feature control frame. Basically, it's about making sure the cylinder pitch's centerline is to fit inside a 1 millimeter cylindrical tolerance zone. And to know where that zone should be, we use datum A and datum B as reference frames. When you're tightening the socket screw into the threaded hole, the screw's center will match up perfectly with the hole's center. Can you actually use maximum material condition on a threaded hole? Just keep in mind that using MMC results in an expansion of tolerance ranges. This means the allowed position error will change, depending on the thread's measured size. Let's start with a simple hole to see how MMC works. The smallest hole size allows for the maximum positional error, up to half the specified position tolerance on the drawing. For that threaded hole, the same rules apply. The minimum threaded hole size allows a positional error of up to 0.5 millimeters. The bigger holes get more space with their location. It's all about fitting things together smoothly, so a larger hole can be a little more off-center than a smaller one. For threaded holes, no matter the size, you get a positional error of up to 0.5 millimeters. This is because threaded holes are all about the centerline, not the fitting boundary. Applying the MMC modifier to the GD&T position of a threaded hole may probably not be the best idea. If we don't need MMC, we can skip applying 0 at MMC as well. So for getting the position tolerance right, it is important to note that the GD&T tolerance of position controls how much it can move and rotate. If the hole is produced with a location error, less than 0.5 millimeters, the socket screw will fit no problem. If the hole is drilled with too much rotation error, the socket screw might not fit correctly. While the error does not impact the engagement of the threaded hole and screw, it will affect the engagement between the clearance hole and the screw body. Because of this, we need to adjust the tolerance zone and move it to the clearance hole instead of inside the part. Essentially, the projected tolerance modifier in GD&T moves the tolerance zone outside the part itself. You always need to specify how far it's projected. In this example, using the modifier P is applied at a distance of 53 millimeters. So the center line of the threaded hole will be regulated beyond the part, ranging from 0 to 53 millimeters from the surface. We've got a new tolerance zone for this thing. It's got the same diameter but is longer than the old one, which makes it tougher to keep the rotational error along the threaded hole's centerline. It's not really ideal yet, since we want the control to happen in the clearance hole. So what else should we add to the GD&T thing to get it right? Okay, if we want to figure out how far something will be, we need to know where it starts and where it ends. For this case, we're using a P modifier with values of 53 millimeters and 46 millimeters. This means we have a clear range for positioning the threaded hole, which covers both translational and rotational errors. This way, the socket screw will align correctly with the threaded and clearance holes. Keep in mind, this isn't the only way to do GD&T. There are other strategies for finding GD&T that might work better depending on things like how parts go together, how they're made and checked, and other details. Thanks for spending time watching the video. Hope you found this helpful and interesting. Looking forward to seeing you again in the next episode.